Hi everyone and welcome back to my channel. So from today onwards we will start a new chapter, that is cache memory from computer organization and architecture, which is one of the most important and highest weightage subjects either in GATE, like for the students who are preparing for GATE CS, or for the placements. Okay, this is not present in the GATE EC syllabus. So for GATE EC you don't need to study it, but if you are preparing for digital VLSI roles, then definitely you need to study this chapter. If you are preparing for GATE CS IT branch, then definitely you need to study this chapter. Okay, these are very important. This is very important topic for these two uh, uh, like uh, uh, branch, like CS IT and EC for placements. Okay, so today we will obviously understand why was cache memory required. Like, we have already known that we have main memory and CPU. Why was cache memory required? What is the meaning of cache memory, and how does the word transfer happens? Okay, those things I will understand. I will explain. So in this lecture 1A, we will discuss about locality of reference. Okay, what do we mean by locality of reference? Memory access time. We will do few mathematical problems on memory access time. Also we will understand cache write policies. Okay, so first of all, let's understand what do I mean by locality of reference. So uh, let's say there are two people, right? Let's say you are there and your neighborhood, whatever your friends house is there, right, near. Let's say you are you are Anish, okay, and your friend is Himanshu. Your friend is Himanshu. Now now there is a, like, there are many people in the school. So one of the guy from the school, he knows Himanshu, he doesn't know you. Okay, so how will you say to him that I, how can you explain that where do I stay? How can I explain it to him? So you will say, look, I do understand you don't understand the address and all those things, but I live near Himanshu's house. I live near Himanshu's house. So I am in the locality of Himanshu. Wherever Himanshu was, I was there. So I used a reference of Himanshu, and then I told that guy that I live near Himanshu. Okay, then that guy will definitely understand because he knows Himanshu. He knows Himanshu. So he will say, okay, okay, got it. You live near Himanshu, got it. So same thing, something similar happens in the computers as well. So how does it happen? I will explain. But let's understand the first definition of locality of reference. Definition of locality of reference is that locality of reference refers to the tendency of the CPU to access the same memory location or nearby locations repeated within a short time frame. Okay, so basically, right, if I have to perform some instructions, right, execute some instructions. So I am doing some instruction fetch from the RAM. Instruction fetch from the RAM. So CPU is fetching some instructions from the RAM, right? Then storing it in its own registers. So from the RAM, I'm doing some instruction fetch. Okay. So if I know the starting address of the instruction, that is 1000, you do understand, right? Like, if I run a program is of megabytes, right? A program is of megabytes. So I will show you just example. Let me open the task manager. Okay, so this is the task manager. So like these are all the different memories. Okay, so this is my CPU. This I have already shown in the course as well. CPU has this speed. It has, if you see here, it has L1 cache, L2 cache, L3 cache. What does each cache mean? We will understand. If you observe very carefully, L1 cache has the lowest storage, L2 cache has the next lowest storage, and L3 cache has the highest storage out of all these three. What does it signify? It signifies that L1 is the fastest, L2 is the level 2, that is the slowest, like not the slowest, slower than the L1, and L3 is the slowest. Okay, so cost reduces. This I have explained in my memory hierarchy videos. Okay, so L1 L3 cache, we will understand what are L1 L3 cache, don't have to worry. So the cost will change, right? Now if I go into memory, so memory is what? Memory is my main memory where actually the programs are stored. Okay, where my programs are stored. I mean, currently whatever programs I'm running, those things are stored in the main memory. So currently, if you see, my memory usage is really bad. Actually, I'm using almost 13.2 gigabytes out of 15.4 gigabytes. Okay, okay, in use is it's okay, sorry, just hold on. 15, is it like 15? Okay, memory usage is out of, yeah, 15.4 gigabytes. I'm using 13.3 gigabytes, which is actually like I use very memory intensive tasks, like multiple Chrome tabs are running, everything is running. Okay, so if you see, let's go to the processes. So there are multiple processes running right now, like Adobe, few other tasks. So if we see each of the processes, how much memory is it taking? So Adobe is taking, let's say, 200 megabytes. Chrome is taking almost 4 gigabytes. Okay, and there are OS things are also there. Okay, so all these are taking the memory. Okay, so it is like 100 megabytes. So what do I want to come to? Like, what is the conclusion? Conclusion is that ultimately, right, it will be not like that. If I am fetching some instruction, it will be only like a 8-bit instruction, right? I will have thousands or hundreds of thousands, millions of instructions. Like it will start from 1000 to some 10,000, something like that, right? Of the same program, correct? So the CPU, like CPU address is very large. It is like a 16-bit, 20-bit address. So CPU understands that if I, this is some place where this all these instructions are stored. So I have to access this programs multiple times, access this location multiple times. Once for 1000, then again after the 1000th instruction is fetched, then I will fetch the 1001, then I will fetch the 1002. So I have to access this location multiple times, and this is stored in the main memory. Okay, so we can actually do one thing. What we can do is, instead of going to this main memory, right, because it takes us time to go to the main memory, what we will do, we can have an intermediary memory known as cache memory, where whatever, like currently I need 1000, currently I am fetching the instruction 1000, which is stored in the location 1000. Currently I am fetching the instruction 1000 that is stored in the location 1000. Okay, currently I am fetching the instruction that is stored in the location 1000. But I do know that just after fetching this instruction, again I have to go to location 1001 to fetch the next instruction. Again after fetching this 1001 instruction, again I have to go to location 1002 to fetch the next instruction, and so on. So if CPU is very smart, and the people who built this thing are also very smart. So what they thought is, what if, yes, I do understand, I have to go to location 1000. What if after going to location 1000, what if we store more values on an intermediary memory from 1000 to, let's say, 1100 or 1200 or 2000? What will be the advantage? Advantage will be, now next time when I will go for fetching the instruction to location 1001, I will not go here. I will directly go to the cache memory, that is the intermediate memory, and I will retrieve it back. You will say, then what's the difference, sir? So anyways, here also we are retrieving the data back. Here also I am retrieving the data back. What is the difference? The difference is this is slower. Main memory is slower. So every time I go and read back from the main memory, time is wasted. So, but advantage is cache memory is very fast, and it is very near, it is strategically very near to the CPU. So data transfer happens very fast. And now you might have the doubt, sir, अगर इतना ही सब कुछ अच्छा है कैश मेमोरी में, if it's so good in cache memory, then इसको ही यूज कर लेते हैं. Why use main memory? Why not use only cache memory? The thing is, of course, everyone wants the best thing, right? Everyone wants the best thing. But the problem is that here it is costly. Right? So anything that you want, it is costly. So anything good that you want is costly. So that's why if I show the task manager, my main memory is 16 gigabytes. Okay, main memory is 16 gigabytes, but my cache memory, if you see, CPU cache memory is only in megabytes. It's so low, right? So low. So just imagine what is the cost. Okay, so you will get mad, right? So you will not buy the laptop then. Okay, because you know that इतना पैसा कौन देगा, इतना पैसा नहीं दूंगा मैं तो, मेरे को तो सब कुछ फ्री में चाहिए. I want the course free, I want everything free. Okay, I don't want to spend any money. So you guys are really like, what can I say? Okay, so really I mean, what do you say, like everything you want, everything in free, right? Everyone wants everything in free, okay? But of course it takes hard work. So this cache memory, making it and getting this many high speeds, the elements that are present inside it are very costly. So that's why it is low storage. So it's not like we can use it as a main memory. So it's not like I can store the whole program, because whole program will be very storage intensive. If you see the whole program, it's like 200 megabytes, 4 gigabytes. Chrome is 4 gigabytes. So it's not like I will be easily able to store it in cache. But near locality reference, whatever the near about addresses, the instructions, those I can store. So that is what the cache memory comes into the picture. So every time I have to go to the memory, right, that waste a lot of time. So to save that time, we use cache memory. Okay, so yeah, I hope practically you understood, and I have shown you the property as well, like all those things, right? Nobody will share you these practical things, okay? They will just say these theoretical things and that's it. But I am sharing you practical things as well. So if you're enjoying, make sure to hit the like button and obviously comment down below, okay? Comment down below how you're enjoying the videos and lectures. So yeah, that was the practical experience that I wanted to give it to you, okay? So now there are two types of locality of reference, okay? Locality of reference you understood, like a near address, how many times I'm accessing it. There are two types of locality of reference. One is the temporal locality, another one is the spatial locality. Okay, one is the temporal locality, another one is the spatial locality. So what is temporal locality? Temporal locality is based on time. So access, if I'm accessing the same location after few milliseconds or like very small amount of time. So what does temporal locality means? Temporal locality means that I am accessing the location frequently. Okay, frequently I am accessing the location. So accessing the same location, so this one, accessing the same location frequently. Okay, I am accessing the same location frequently. So if I'm accessing, let's say I accessed 1000 location at t equals to 0 nanosecond, then again I access 1000 location at t equals to 10 nanosecond, again I access the 1000 location at t equals to 20 nanosecond. So I'm accessing it multiple times, right, after regular intervals. That means there is a high probability again I will access it. There is a high probability again at t equals to 30 nanosecond or at 40 nanosecond, again somewhere I will access it. So these are known as temporal locality. Okay, if a specific memory is accessed, it is likely to be accessed again soon. Okay, this is known as temporal locality. Now what is spatial locality? Whatever I have explained, right, this example, that is known as the spatial locality, that I will access the nearby location. Okay, it is based on space, based on the address. So basically I will access the nearby location, access the nearby location. So what does it mean basically? It basically means that if I have accessed location 1000, that means I will definitely access location 1002. Like there is a high probability, that CPU will access any location near 1000 again. So I will write here, if CPU has accessed location 1000, there is a there is a high probability I will access location, I will access nearby location location of 1000 again. Okay, so now, like whatever I have explained, those things are written over here. Basically the cache memory importance and usage importance of locality reference in cache memory. So cache memory is the on chip memory that is attached with the CPU, so it is very near to the CPU. It is very near to the CPU. That's why if I show you the task manager, that there is no separate tab for the cache memory, right? There is no separate tab for the cache memory. If I go into the CPU tab in the task manager, cache memory is directly here, L1 cache. So it is stored very near to the CPU. Okay, this memory, right, is not stored near to the CPU. Someone who has installed RAM chips or something, he or she will understand that we can like RAM chip is somewhere else and we just install it. It's like a stick, right? We install it. Okay, but if someone can tell, like if, obviously you guys will understand that you will not be able to change the cache memory. Cache memory is fixed with the CPU. Okay, cache memory is fixed with the CPU. This is never upgradable. You can never upgrade the cache memory. You have never heard anyone saying that I want to upgrade my cache memory. You have never heard of this term. You have definitely heard that the RAM is upgradable. You have definitely heard that the hard disk is upgradable. All these things are upgradable, but you have never heard that cache memory is upgradable. So memory is upgradable, but cache memory you have never heard, right? So it's very close to the CPU. So that's why sometimes cache memory is also called as on chip memory, because chip is the CPU. So it is also called as on chip memory. On chip memory. So basically it is attached with the CPU. Attached with CPU. Okay, so let's read. Cache is smaller, faster memory designed for the concept of locality of reference. When CPU accesses a memory location, the corresponding block, like near about locations, right? And if it either if it is a temporal locality or if it is a special locality, that thing is stored, that block is stored in cache memory. So data in cache memory is stored in blocks. Data in cache memory is stored in blocks. Okay, so like there is another analogy for cache memory as a bookshelf. Imagine your desk has a small bookshelf. Okay, your desk has a small bookshelf for frequently used books. So near your desk you have small books, which let's say you are currently studying in class 10th, right? So if you are currently studying in class 10th, so whatever books you use in your class 10th, those will be there. Or if you are in engineering first year right now, so whatever book you engineering, let's say first year, whatever are the subjects of your semesters, so those books will be stored in the your desk bookshelf. Now you have a larger bookshelf, larger library, which is used to store the less frequently used books, like let's say your previous books, right? Class 11 12 books, because class 11 12 books can be required. You are studying engineering, right, in ECE, so electrical concepts like circuits, all those things you have also studied, right? Basic EMFT, those subjects you have studied. So maybe one day you may require it, but it's not like you will require it frequently. You might require once or twice, correct? So the less frequent books are stored in the bigger bookshelf. Less frequent books are stored in the bigger bookshelf. Okay, so if the book you need is on the shelf, you access it immediately. So now the important factor is, let's say you are at your table, you need a book. So what is the probability, like which one has the higher probability, you needing the engineering book or the class 11th or 12th book? You will say, sir, having requiring the engineering book has the higher probability. Requiring the engineering book has the higher probability, because of course currently I am in first year engineering. Okay, first year of engineering. So of course I will require a book from the first year semester, whatever subjects are there, right? 11th and 12th book may be required, because let's say I'm in first year of my engineering and I am not able to understand a particular concept which involves a bit of learning about the 11th and 12th science concept, right? So then I will go to that. Okay, so that has lower probability. So there is a term known as cache hit. What is cache hit? Cache hit is you need a book. Okay, you need a book and you got the book from the small bookshelf, from the cache memory. You got the book from the cache memory. That means it is a cache hit, right? Because I needed a book and I went to the bookshelf and I got the book. So it is a cache hit because it was a memory hit. Whatever I required was given to me. What is cache miss? If the book is not in the shelf, let's say you required a book and it is not your first year engineering book, it is a physics book of class 12. So you will first go to the cache memory. You will ask cache, do you have the class 12 physics book? Cache will say, no bro, I don't have the class 12 physics book. So that is a cache miss, right? You went to the cache memory and the cache, like you are not able to get the book, right? That is a miss. That is a miss from the cache. So that's why it is called as cache miss. Cache miss. Okay, that's why it is called a cache miss. Got it? Cache hit and cache miss. If I go to the cache memory and whatever I required I got from the cache memory, that is termed as cache hit. If I went to the cache memory and whatever was required I did not get, that is known as cache miss. Got it? Now just one small thing, that this is my main memory, right? This is my main memory. Okay, and in between I will have cache. In between I will have cache. Basically, let's say once the CPU required this memory location. So if it required only this memory location, right, what the cache memory will do, it will store all these locations in the cache memory. Why? Because all these are locality, and CPU does understand if I am requiring this location, maybe I may require the next location next time, maybe I require the previous location. It is a possibility because it is a spatial locality. So that's why I will store it in the cache memory. So next time when I will go and look for the data, I will store it here. So basically what happens, so practically what happens is initially everything is empty. Okay, now if everything is empty, first CPU will go to the cache memory. So the first task of CPU is going to the cache memory. So first we go to the cache memory and I ask the cache memory, cache, do you have the instruction stored in location 1000? Cache will say, no, I don't have the instruction stored in location 1000. So then what will happen is we will transfer the instructions stored in location 1000 and few more data as well near about that address location 1000, that will be stored in the cache memory. After that happens, then finally the data will go from cache memory to CPU. So CPU, right, actually never goes to the main memory directly. CPU never goes to the main memory directly. CPU always goes through the cache memory. CPU always goes through the cache memory. Okay, so that is the important point that you need to understand. CPU always goes through the cache memory. Okay, so yeah, I have explained you basic working of cache memory. So there are few terms that I already explained. Cache hit. Cache hit is the requested data that is found in the cache, and cache miss is the requested data that is not found in the cache. So it must be fetched from the main memory to the cache. So basically, right, this is how the data transfer happens. So either the data will be fetched from the main memory and it will be stored in the cache memory as well as the CPU, or if it is already present in the cache memory directly, the data will be coming from the cache memory only. Okay, so this is the basic block diagram. Now there is a term performance metric known as hit ratio. Hit ratio is what? Hit ratio is the number of cache hits divided by the total number of memory reference. So let's say I have referenced the memory 1000 or let's say 100 times. Out of 100 times, there is 20 times when I went to the cache memory. Out of 100 times, total I went to the cache memory 100 times, and out of 100 times, 20 times was a hit. Basically whatever I requested I got that, and other 80 times was a miss, right? So whatever I requested, it was not present in the cache memory, I had to go to the main memory. Okay, so what is the hit ratio? Hit ratio is basically each number of hits divided by the total number of number of hits divided by the total number of memory references. So how many times I require the memory reference? 100. What are the total number of hits? 20. So it will be 0.2. Okay, 0.2 will be the hit ratio. Basically 0.2 will be the hit ratio. Okay, so what are the limits? What is the miss ratio? Miss ratio is just the inverse of hit ratio. Basically number of miss by total number of memory reference, or it can be written as 1 minus h. Why 1 minus h? Because what is the maximum limit of h? Maximum limit of h is 1 and lowest value is 0. 0, how? 0 number of hits. 100 times I went to the cache memory and 100 times there was no hit, there was miss. So I was not able to hit any time. So that's why 0 by 100 will be 0 only. So that is the lowest value. Obviously it cannot have negative number of hits, that is not possible. Now I went to the cache memory 100 times and I was very lucky. There were all 100 hits, all 100 were hits. So I did not need to go to the main memory even once. Okay, so hit ratio will be between 0 to 1. So can you tell me which one is better? Like having higher hit ratio is better or having lower hit ratio is better? Of course, having higher hit ratio is better. So if my hit ratio is better, that means my data transfer will happen very fast. I don't need to go to main memory multiple times. So higher hit ratio is better. Higher hit ratio is better. Okay, having higher hit ratio is better. Now like there is another analogy for cache hit and cache miss. So let's say you are working on a research project and you need books to complete your task. Here's how cache memory will work. Cache hit, you first check your desk, right? You're working on a research project, so first you check your desk. So whatever books are present, if the book you need is there, that means you have found the book and you continue working immediately. You don't need to go out of the table, you continue working immediately. So cache hit is very quick and efficient. That's why higher the hit ratio, the better the system will be. Now what is a cache miss? Cache miss is if the book is not on your desk, you visit the library and then retrieve it. So you visit the library, then either you like you met with a friend, okay, and you started talking, or let's say you're like you went, like when you were at the desk, your phone was silent, right? Now you went to the library and your phone was in the general setting, so a call came from your girlfriend or boyfriend and she or he asked like what you're doing. So you said I'm in the library. Then she will say I will also come to the library. Okay, so then basically you don't come back to do your work, right? You do everything else except your work. So there is an interruption, so there is time wastage, right? So that is what happens if there is cache miss. So if there is cache miss, you visit the library to retrieve it. So while you are in the library, so so that is about the wastage part, okay. But let's understand actually what happens. So actually if you are in the library, right, so what you will do, you are a very smart person. So if you knew that in the desk that book was not there, so let's say there you need a book related to theory of relativity, okay, relativity. So what you will do, of course you will go to the library and get that exact book. Also you will get few other books which are related, and then you will store it in your desk. You will keep it in your desk, because you know maybe while studying this relativity concept, maybe this book is not enough, I may need to study any other book as well. So you will take other books as well and you will keep it in your desk, so that next time if I again need more information about relativity, I don't need to go to the library, I can directly take the book from my desk. So that is what is written over here. So while at the library you decide to bring back not just a book you need, but also few other related books nearby memory address. So in computer terms, technical terms, it is the nearby memory address. So once you went to the memory 1000, okay, it's not like only you need the memory 1000. Once you went to the main memory 1000, once there was a cache miss, you went to the main memory 1000. So you are smart, so you will say, don't just bring the memory 1000, bring near about 30 to 50 memories near the memory 1000. Okay, so that is what my that is what happens in a cache miss. Technically that is what happens in a cache miss. Okay, now the fetch books are placed on your desk for quicker access for future reference as explained. This is a cache miss, slower but prepares for the future needs. So yes, cache miss is slower because you are again transferring higher number of data, right? Cache miss is slower because again you are transferring chunk of blocks of data. That is fine, but you are future proofing yourself for the future. Basically next time if you need any book related to relativity, you will not go into the library again, you will not procrastinate, right? Again, call from your girlfriend or boyfriend will not come because you will keep your phone on silent and you will focus so on the desk. So to avoid that, that's why we bring chunk of data together, so that if I require the data next time, I will directly get it from the cache memory. Now there is another concept about cache replacement. What is cache replacement? If your desk is full, you must remove some books to make space for the new ones. So now relativity books you have kept and your desk is full, right? You don't have any space to keep new books. But now let's say you are studying a new concept, quantum physics or quantum mechanics, right? Quantum mechanics. So now if you are studying quantum mechanics, so you will need books related to quantum mechanics, but you don't have space. So what you will do, whatever books you had in the book, those you will remove and keep it in the library and bring the new books, because now you need quantum mechanics, right? Now you don't need, you will need relativity, you may need relativity, but right now what do you need? Right now you need quantum mechanics. So you will bring those books to you. Okay, so you will need quantum mechanics. So that's why what you decide to remove the least recently used book. So it may so happen you required relativity, then you required some other book, some finance book, anything, right? Finance book, some management book. Okay, then you required quantum mechanics book. So what was the least used, like least recently used? So least recently was this one, right? This you used way back. So whichever was the least recently used, that it will kick out of the memory. Something similar actually happens in our like of what in our computers. This only happens. So like I will explain. So here, right, the CPU is here, and if I show you the task manager, these are my tasks, right? And in your phone as well, if you want to see in your phone as well, something similar happens. That currently what are the apps? Adobe, Glide, Google Chrome, OBS, these are the apps, right? So let's say my RAM becomes fuller, right? It becomes more and more fuller. So what RAM will do is it will remove the apps which are currently running. It will remove those apps because of course RAM has only 16 gigabytes of capacity. I cannot open infinite amount of apps. So what RAM will do, whichever one process was like stored in the main memory, the oldest, that it will automatically kick out. Same happens on your phone as well, right? In your phone, if you remember, if I run 4 or 5 games, right, let's say PUBG and all those things, so whatever game you had opened recently, that will stay in the RAM, but the games which were there 2 3 opens, like let's say I opened first, I opened Subway Surfer, then I opened PUBG, then I opened Firefight, something, Firefight is the name, right? Then I opened, what is the other name, Fortnite I opened, then Call of Duty I opened. Okay, so the first game that I opened was Subway Surfer. So once I open Call of Duty, right, my CPU in the phone will understand that it does not have enough RAM, so it will automatically kick out the Subway Surfer. Then again, if I open a new game, again whatever was the oldest one that I opened, least opened, that it will kick out. So that is how our cache replacement occurs as well. Least used thing will be kicked out. Okay, now you might say that, sir, that also may be required. Yes, that also may be required, but we are playing a game of probability. We are playing a game of probability. That may be like, it is the least probable thing that may be required. Okay, so this kind of replacement policy is known as the least recently used. Okay, so the name is least recently used. I hope from the name you can understand why is it called least recently used. Whichever one was used least recently, that will be kicked out from the cache. Okay, so it is less likely to be needed again. It can be needed, it can be needed, but we assume it is less likely to be required. So how does it improve the efficiency? The desk reduces the time spent traveling to the library and wasting your time on phone by predicting future needs. Of course we can go wrong, but it will optimize the performance and system delays. So I hope now you have understood how cache memory improves the performance, and like what is LRU. We'll learn about LRU later on in this lecture itself. So now let's learn about few more topics. So this is the another topic that I wanted to discuss here about the average memory access time. So what is my average memory access time? So average memory access time, right, is equals to h into t hit plus 1 minus h into t miss. And I know you don't understand anything here. I do understand you don't understand anything here. So I will explain one thing at a time. So average, right? So I have to find out average. So how do I find out the average? How do I find out the average? So actually average will be the average access time will be equals to the number of hits number of hits in the cache memory. Like there can be either two things, right? In the cache memory there can be either two things, either I have hit or I have missed. If I have hit, if it is a hit, that means how much time will it take me? It will take me only the time it will take me is the cache memory access time. Okay, it will take me only the cache memory access time. If I have missed, that means that particular data or block is not in the cache memory. If that particular data or block is not in the cache memory, then I have to go to the main memory and then bring the block to cache memory. So how much time does it take? It will take somewhat more, right? It will take somewhat more. Okay, it will take somewhat more. So basically I have two things here. So the first thing is, let me just reduce this. So number of hits. So out of, let's say, total 100, right? 100 attempts. Let's say I had 30 hits, or like let's say out of 10 attempts, I had 4 hits and 6 miss. Okay. So if it is 4 hits and 6 miss, then basically it means that what will be the average access time? Average access time, T average, will be equals to 4 number of hits into the time that the cache memory takes for the data to give it to the CPU. So T cache, or this is also written as T hit time. Hit time is generally lower than the other one. So plus 6 into T miss. Okay, T miss plus 6 into T miss. Basically whatever time it is taking me to find out T miss. Now what is T miss? That will be cleared later on. So here also same thing is written something, but this formula is completely different than what I am writing here. Don't worry, we will get to this formula. Okay, just understand this thing, that this T miss is not just a single number. This T miss is a combination of many things that we will understand as we move along the chapter. Okay, so T average will be equals to 4 into T hit plus 6 into T miss. So this is the total time taken for 10 memory access divided by, so we have to find out the weighted average, divided by 10, right? Because I had done 10 memory access. So this will be equals to what? T average will be equals to 4 by 10 or 0.4 into T hit plus 0.6 into T miss. Okay, so this is 0.4 into T hit and this is 0.6 into T miss. Okay, so this is my T average. This is my T average. Okay, now the important point is, what is this actually 0.4? This 0.4, if you remember, is actually equal to what? This 0.4 equals to 4 by 10. So it is equals to number of hits by total number of memory access. That is what? That is my hit ratio. That is my hit ratio. So that's why this term is present over here, hit ratio. What about this? What is 1 minus h? It is the miss ratio basically, and miss ratio is 1 minus h, which is written over here, right? Miss means number of times I have missed the cache, that is 6, divided by the total number of times, that is 10. So it is 6 by 10, that is 0.6. So that is my miss ratio. So hence it will be 1 minus h. Got it? So this will be always 0.4, 0.4, 1 minus 0.4 is 0.6. So that's how this formula came. Don't worry about this T miss. T miss will be, we will calculate the T miss together. So for this T miss, right, we simply have to read, for calculating of T miss, we have to read the question. Read the question. Okay, for calculating the T miss, you have to read the question. Got it? Okay, so we will solve it. Don't worry, we will solve it. So this is basically the formula, general formula for T average. This will keep on changing as we move along. This will keep on changing. So it's not like you remember mug this formula. It will keep on changing. Okay. So there are many types of cache access. So the first type that we will learn, like the first two types that we will learn, is simultaneous access and serial access. What does simultaneous access and serial access mean? Okay, let's read. Cache and main memory are accessed at the same time. So basically, let's say my cache memory is here. This is my cache memory and this is my main memory. This is my cache memory and this is my main memory. So what I can say is that, let's say I require the, like this value I require, right? Let's say this data at address 100 is there and I require this 100, and let's say cache contains the value like address of like 110, 120, something like this, 130, but it does not contain 100. Cache does not contain 100. Okay, so I am CPU and CPU is asking that I need the data stored in location 100. So I went to the cache first and then I see that it is not present in cache. Then I went to again main memory. So the time taken, right, to go from the CPU to cache, I can do a bit of shortcut. What kind of shortcut? What I can do, the moment I start looking for address 100 in cache, same moment I will start looking for address 100 in main memory. Okay, simultaneously at t equal to 0, I will go from here to cache memory, and at the same point I will go from here to main memory. Yes, I know the doubt that both of these times are not same. Yes, they are not same. It will take me more time to reach main memory than to reach cache memory. Why? Because cache memory is nearer to the CPU than main memory. Next, what I will do is, if I have a cache miss, like I went to the cache memory and I got to know that it is actually not present. Address 100 is actually not present in the cache memory. So if address 100 is not present in the cache memory, what you will do is you will send a signal that to the other guy, like there are two guys, one is Ram and this is Sam. Okay, so Ram will tell to Sam that I went to cache, but cache does not have this value, address at 100 data. Okay, please you bring back, like you bring the data, right? I don't have the data. So advantage here is, let's say it takes me 10 nanoseconds to reach from my CPU to cache memory, and it takes me 30 nanoseconds to reach from this CPU to main memory. So after 10 nanoseconds, I got to know that okay, the data is not here. Data is not here. If the data is not here at t equals to 10 nanoseconds, Ram tells to Sam that data is not present in cache memory. You are already in the midway here. Okay, please continue and go and bring the data. So basically I save my 10 nanoseconds time here, right? Because I am already in the middle. Okay, I'm already in the middle. So I only need 20 nanoseconds to reach to the main memory. Previously I waited for the cache. First I checked here whether it is present or not. If it is not checked, then Ram tells Sam, okay, it is not present. So Sam starts from here. So it will take me 30 nanoseconds. So what is the total time savings? 10 nanoseconds. Or it is the time savings of the T main memory T main memory minus T cache. Okay, T main memory minus T cache. So this is the time difference, right? This is the time difference. So now the thing is that this I will implement. So that is what happens in the simultaneous parallel access. But the next doubt will be, what if there is a hit? So if there is a hit, right, there is no loss. If there is a hit, there is no loss. So once RAM reaches here, and let's say now I require, CPU tells now I require location 120. So both start same, okay, both start from the same starting point, same time instant. RAM reaches here faster, 10 nanoseconds, and he checks, okay, 120 is present actually. 120 is present in the cache memory. So if 120 is present in the cache memory, then RAM will tell Sham, bro, I got this. You don't have to do any hard work. I will bring the value 120 to CPU. You can sleep now. Okay, you go back to sleep. So there is no wastage. Okay, it's fine. So Ram had gone until traveled this path. He will just return back. That is fine. That is fine. Okay. So there is no harm. Okay, of course, like there is harm. There are advantages and disadvantages. I'm just explaining you. It's okay. It's totally fine. It's not that big of a deal. So here, that is what my parallel access is, right? So I access it at the same time. So that's why my T average here will be the, what will be the T average? T average formula is H into T hit into T miss. So if it is a hit, right? If it is a hit, that means there is a cache hit. So whatever time it takes me to reach to the cache memory will be the T hit. Okay, whatever time it takes to reach the cache memory will be my T hit, that is T cache. What if it is a miss? If it is a miss, that means first of all it will be 1 minus S H, because it is a miss, into the access time of the memory, into the access time of the main memory. Now you will say, what is the difference then? Previously also it was taking the access time of the main memory. This we will understand once we will see the hierarchical access. Okay, what is the difference? We will see. So overall, how much time is it taking me? So basically, if you see here, right? So from if I observe from t equal to 0, how much time it will take me if I miss? So actually here after 10 nanoseconds, I got to know that it is not present in the cache memory. It is not present. So just it will send a signal to Sam that it is not present. You continue. So Sam will continue. It has already consumed 10 nanoseconds. It will take another 20 nanoseconds and get back the data. So overall, how much time did Sham took? 30 nanoseconds. It is equals to what? It is equals to the main memory access time. It is equals to the main memory access time. I will tell you what is the difference, right? In serial, we will see the difference. Okay. So here this will be T memory. So here the T miss can be anything. T miss will be T memory here. Generally the T hit is equals to cache memory time only, but T miss can be anything. T miss can be anything. Okay. So yeah, that is one more thing. Now what about the hierarchical access? What about the hierarchical access? So the hierarchical access is like is the serial access. Okay, serial access means first cache is accessed first and main memory is accessed only if there is a miss. So first RAM goes to the cache memory. If it is a miss, then we tell Sham to start. Sam doesn't start until RAM tells that okay, I have not got the value in the cache memory. So it is serial. It is not simultaneous, it is serial. Okay. Why? Because first RAM will go, then it will tell Sham. So now how much time it will take me? If it is a cache hit, then there is no problem. If it is a cache hit, then there is no problem, right? First RAM will go, it will take its 10 nanosecond. Let's say I want memory 120 and it is present in the cache, it will give back to the CPU. So this part is same, this part will not change. But what will change? Let's say if I wanted the location 100. Now if I wanted the location 100, now what will happen? If I wanted the location 100, it is present only in the main memory. So first RAM will go here and RAM will see that location 100 is not actually present here. The data location 100 is actually not present. So what RAM will say to Sham was sleeping here. RAM will say, bro, wake up. Now start your journey. You have to go to the main memory and bring the location 100. Okay, because Sam was sleeping. So now at t equals to 10 nanosecond, Sam will start his journey from here. Now how much time will it take me? Again, I have to cover the same distance, right? It will take me another 30 nanoseconds. So 10 nanoseconds is there for the cache memory access time, because RAM has to know whether it is present in the cache or not. Like obviously from the starting itself, I will not be able to predict, right? We are not able to predict the feature whether it exists in the cache memory or not. I have to go to the cache memory, then only I will be able to say whether it exists or not. So that's why I have to go to the cache memory. So it took me 10 nanoseconds to go to the cache memory, plus if it is a miss, additional 30 nanoseconds it will take me to go to the main memory. So that's why here it is cache memory. If I have a miss, it is the cache memory access time plus the T memory. So that is the difference which I told here, right? The difference between T main memory and T cache. The difference is T cache basically. I hope you got the answer, right? Basically the difference is T cache. So T cache will be the extra time that will be required in the hierarchical access. Of course, everything has its own advantage and disadvantage. We will see those. Okay, so yeah, this was the thing about the simultaneous access. So there are now, right, one more thing, one more important point is this. I just told you for one particular address, right? One particular address, if I want, this is the transfer time basically. But of course, when you basically transfer anything to the cache, right? When you transfer anything to the cache, like also one more thing, generally if it is a miss, right? If it is a miss, I go back to the main memory, I copy to the cache memory, also into the CPU. I copy it to the cache memory and also into the CPU, right? Okay. Now, as I have already told you, each program is of megabytes. Okay, each program is of megabytes. It's not like I will go and just bring one data, right? One address. It's like your father has told you to go to the market. Your father will not just tell you to buy, like if you need one egg, your father will not tell you just go to the market and bring one egg, right? Your father will also tell you, your father will see the house, see what are the other items or food items, whatever is required. If something extra is required, also father will tell you to bring those as well, if even if it's present in the house currently, but it will finish up, so your father will tell you to bring those as well. So of course you are going into the market, of course you will not just bring one egg, right? You will bring a lot of things, right? So same is here as well. If Sham is traveling to the main memory, Sham will just not bring the 100 address, because I have to store it in the cache memory. Sham will bring the locality reference. So in cache memory, in technical terms, Sham will bring blocks of data. So we will bring blocks. So in cache memory, blocks of data is transferred. So in cache memory, blocks of data will be transferred. It's not like I will just access one address location, right? So that is the advantage here. So I hope you have understood this basic point. Point. So if it is without block transfer, then you don't have to worry anything. Whatever I have told you, the same formula remains. But if it is with block transfer, let's say to transfer only a single element, it was taking me 1 nanosecond, but now I am transferring like two elements. How much time it will take me? 2 nanoseconds. So if I am transferring, if the block size is the size number and to transfer each element is t main, then the total transfer time to transfer the block will be t block into, it will be block size into t main. Okay, that will be the total transfer time of block size. Okay, and what about the simultaneous access? So simultaneous access, like now let's see the block time with the simultaneous access and the hierarchical access. Okay, so in simultaneous access, the average time, hit time is same, right? It will not change. It will be h into t cache. Very rarely change. It does not change. If it is a miss, it will be 1 minus h into t block. So basically, right, if I am going to the cache, if I am going to the main memory, I will bring a block of data into the cache memory. If CPU is asking for value stored at address 100, so if I go to the cache, it will only bring that. So let's say you are at your home, so your father is asking you to bring a egg, your father is asking you to bring a egg, okay, bring a egg. So you will go to the refrigerator, you will bring that single piece of egg, correct? But let's say you went to the refrigerator and there is no eggs left. So there are no eggs left. If there are no eggs left in the fridge, what you will do? You will go to the market. Will you bring only single egg? Will you bring only single egg, or you will bring 6 or 8 eggs? Like if I was at the home, I would have bring 6 or 8 eggs, because I know of course one egg would not be enough, right? I need more eggs. So, like it will be required. So same thing here. Same thing here. So here also, if I am at the home, then I will only bring one, whatever is required, that I will bring, right? If I am going into the market, I will bring multiple things, because I don't want to go to the market multiple times. Same concept is happening here. So like same analogy I will give. So if I am at home and home is I required a egg, okay, single egg. So I will go to the fridge. Fridge is my cache memory. Fridge is my cache memory. Okay, fridge is my cache memory. So if the egg is present, then that's it, I will bring the egg here, right? If the egg is not present, of course I have to go to the market. This will be the market. Okay, in the market, it's not like I will only bring one egg, I will bring 10 eggs or 20 eggs, something like that, right? So I hope you got the point. Here also, if it is a miss, I will bring block of data into the cache memory. So next time if I require something similar, I may found it in the cache memory. That is the main purpose of cache memory, right? So that is what we do. So it is T block into T cache. T block is the time required to transfer a block of data from the main memory to the cache memory, okay? And plus the T cache. Why T cache? So once I have transferred it back to the cache memory, how much time is it taking me to transfer that data, whatever I required, from the cache memory to my CPU, okay? So this will actually be here. This will previously, right, there was only, if you see, there was only T memory. There was only T memory here. Now T memory has changed actually. T memory has changed. How? Why has T memory has changed? So T memory has changed because it is equals to T cache plus T block. So basically this is the time required to transfer one block, transfer block of data from main memory to cache, and this is the time required to bring it from the cache, to bring the data from cache to main, okay? But what is happening in hierarchical access? In hierarchical access, what is the problem is, if it is a hit, that is fine, there is no problem. But if it is a miss, okay, so this is wrong actually. This will be, my bad, sorry. This will be not T main actually, this will be T cache, right? This will be T cache, I'm sorry. This will be T cache. So basically what is happening over here, is that first of all, I am, like previously, right, that extra time was not taken. Basically, previously, both Ram and Shyam simultaneously were going. As soon as Ram got to know that, okay, it is not present in the cache memory, it sent a signal to Sam, and Sam directly have given the, it has transferred the block of data from the cache to main memory, at, like, both start from t equal to 0. But in hierarchical access, what will happen? Both will not start from t equal to 0. First, Ram will go, okay, in the cache memory. If the object is present, that is fine, great, it will be h into t cache. If the object is not present, then 1 minus h into, now how much time will it take me? I have to first of all go to the first of all, it will take me t cache. Why it will take me t cache? Because I have to take into account the time taken by Ram. So this is the time taken by Ram for him to say that it does not exist in the cache memory. So this is the time taken by Ram. I hope you remember, right? What is Ram? Ram is always going to the cache memory. Shyam is always going to the main memory. So time taken by Ram. So first Ram will go to the cache memory, then ultimately tell sham that it is not present. So sham, you start your journey. So sham will go to the main memory and bring a block of data to the cache memory. How much time it will take me? T block. It will take me T block. So this is the time taken to bring a block of memory, in cache. Okay. After that, my CPU, again RAM will go from the CPU, RAM will go get the value from the cache. So no, not exactly that. So this is just the transfer time. Bring the block memory. I will just rephrase this. Actually, there is a good term. So transfer. This is the transfer time. Transfer time taken to transfer a block. Transfer a block of memory. Transfer a block of memory. Okay. So this is the time taken to transfer a block of memory. Now, next is this is the time to transfer a block of memory. Next is I have to write it to the cache, right? I have to write it back to the cache. So to write back to the cache, it will take me another T cache time. So this is the write back to cache memory. Write back to cache memory. So roughly they are similar only, writing to cache and reading from the cache. So that's why these are same. Write back to cache. Okay. But here, right, what was happening? Only this part was there. Basically, this bring cache main memory. Basically, this was the write to the cache, right? This was happening here. Write back was happening. Okay, write back to the cache. Write back to the cache, and this was right the time required to bring a block of data into the cache memory. But I did not have to waste this extra cache. I did not have to wait for T cache for RAM to check whether it exists in the cache memory or not. I started instantly. When RAM went, sham also went. Okay, so that's why there is a difference of T cache. Got it? So I hope that portion is cleared. Now let's solve a very basic question on this. So this is the first question. Assume for a certain processor, a read request takes 50 nanoseconds on a cache miss. So if it is a miss, it takes me 50 nanoseconds. So T miss equals to 50 nanoseconds. Okay, T miss is equals to 50 nanoseconds and 5 nanoseconds on each cache hit. So it takes me 5 nanoseconds on each cache hit. So if I have a cache hit, it takes me 5 nanoseconds. So this is the simplest one. Suppose while running a program, it was observed that 80% of the processor's read request result in cache hit. So what is the hit ratio? Hit ratio is 80%, or numerically it is 0.8. Okay, the average read access time in nanoseconds is, what is the average read access time? So average read access time will be what? It will be H. If I have hit, it will be, what is the hit ratio? 0.8 into the time it takes me to bring that data into the CPU. If it is a hit, it is 50. If it is 5 nanoseconds, right? And plus if it is a miss, that is 1 minus h, that is 0.2. How much time it takes me? It takes me 50 nanoseconds. So the simplest one, very simple question only. So this will be 0.8 into 5. So this is 4 nanoseconds. Plus 5 into 2. So this is 2 into 5, that is 10 nanoseconds. Okay, so it will be 40 nanoseconds. Okay, So 14 nanoseconds will be the answer of this question. Very simple, very straightforward, not that difficult. Okay, now let's go to few more bit of difficult question, right? So yeah, let's read this. In a two-level memory hierarchy, the access time for it, the top level is 20 nanoseconds and for the bottom level is 80 nanoseconds. Basically what they are telling me is that top level means like I have two levels. Two levels means one is the cache memory, one level is the cache memory which is more nearer to the CPU. So this is the level 1. Another one is the level 2, that is further away from the CPU, that is the main memory. So you can understand it like this. Okay, main memory. Now what they're telling me is that uh, access time for the top level is 20 nanoseconds. So accessing from the CPU to the cache memory, it takes me 20 nanoseconds. So T cache will be 20 nanoseconds, and T miss, right? What, sorry, T main memory. What is the T main memory? T memory T memory equals to 80 nanoseconds. T memory equals to 80 nanoseconds. The hit rate at the top level is 90%. So basically cache hit rate, it is telling me top level is this L1, right? So cache hit rate is 90%, that is 0.9. It is 0.9. If the cache block is 8 bytes, so basically I store data in cache, right? Data is stored in blocks of data. So each block is 8 bytes. So block size is, they have told me what is the block size. Block size is 8 bytes. Okay. What is the average memory access time? Now they are asking me what is the average memory access time. Okay. Okay. So if they have not mentioned anything about like simultaneous access or the, what do you call that, or the what do you call, or the like hierarchical access, what you will do is you will assume it to be a simultaneous access. You will assume it to be a simultaneous access. If nothing is mentioned, you will just directly find out the this concept. They will generally, from the question you will understand, don't worry, as we solve along the question you will understand how much time it will take me. So let's make this question even more interesting. Let me add in the 2 points for a, the first one, that is this simultaneous access and the hierarchical access. So if it is simultaneous access and it is hierarchical access. Okay, so there are two kinds of access here. So what we will do is sorry, I made the spelling wrong. This will be HIERARCHAL. Okay, HIE. Okay. Okay, so if it is simultaneous access, right, basically it will take me what time? First of all, understand conceptually. If it is simultaneous access, my T average will be what? First, if it is a hit, that means it will only take me the T cache time, right? Whatever time it took me to reach to the cache memory, that is what it will take me. If it is a miss, 1 minus h. If it is a miss, right, and if it is simultaneous, that means I don't waste my time waiting for the cache memory, waiting for RAM. I don't waste my time waiting for RAM. I directly start. So I directly start the block transfer. So it will be T block. I directly start the block transfer, right? T block. If it is a miss, I directly start the block transfer plus the time it takes me to write to the cache memory, T cache. Okay, T block and T cache. Okay, So what is my T block? So let's write the things down. So this is the A part. Okay, understand it conceptually. Don't just mug up the formulas. Understand it conceptually. Okay. So basically, uh, H I know, T cache I know, T mem I know, but block size is 8 bytes. So what will be the T block? Because I don't know T block, right? T block is basically the time it takes me to transfer the block in the from the main memory to cache. Main memory takes 80 nanoseconds. What is 80 nanoseconds? So 80 nanoseconds, right, is basically to transfer single byte of data. So generally we transfer in bytes. So 80 nanoseconds is the time for us to transfer single byte of data. So how much time will it take me to transfer 8 bytes of data? It will be 80 into 8. So T block will be 80 into 8. So this total overall will be 640 nanoseconds. This will be the total T average. Sorry, not T average. Sorry, this will be the T block. This will be the T block. Okay. So this is the T block basically. Now I got all the information, right? I got the T block. I know the T cache. I know the H is 0.9. So now let's just solve. So T average will be in this case 0.9 into the T cache. T cache I guess is 20 nanoseconds. So this will be 20 plus 0.1 into T block. T block is 64 plus T cache. T cache is 20. So here, right, we write in cache memory blocks only. So it will be only write back time will be almost similar to 20 nanoseconds because cache memory is very fast. So it will not be like 8 into 20. It will not be like 8 into 20. It will be 20 nanoseconds only because cache memory is very, very fast. It will not take us more time to write back to the cache. Got it? Okay. So it will be 20 and this will be equals to 18 nanoseconds plus this is 660. So this will be 66. So this will be 4, 24 and 84. So 84 nanoseconds will be the answer. Yeah. 84 nanoseconds will be the answer of this question. Am I correct? 660. Yeah, 8 into 8. 18. Let me just quickly use the calculator. I don't want to mess up here, right? So let me just quickly use the calculator. Just give me 1 second. So it is 0.9 into 20 plus 660 into 0.1, 84. Yeah, 84 is the correct answer. So 84 will be the answer of this particular question. So I hope you have understood this particular concept. Now what if it is hierarchical access? What if it is hierarchical access? So if it is hierarchical access, B part, okay, this was for the simultaneous access. Simultaneous. Now let's do for the hierarchical access. Okay. So for the hierarchical access, basically we have to do one thing, that everything else will be same. This will concept will be same only. Just that when it is a miss, I have to wait extra T cache time because sham does not start until RAM tells him that we don't have that particular value, right? We wait till RAM, so it will be another additional T cache. So whatever here is same only, this is same, except just one difference will be there. What will be the difference? Difference will be here I will have extra additional 20 nanoseconds added. So this will be 20 nanoseconds extra added. So this will be 84 nanoseconds. Okay, so this will be T average will be equals to 18 nanoseconds plus this will be 680, so 68, so this will be 86 nanoseconds, 86 nanoseconds. Okay, okay, so I hope you have like you have understood this particular thing. So that's how you solve. So I will just make one small change here in the assignment questions, because in the assignment questions also you guys will have doubt. So two parts is there. A is for the simultaneous access, simultaneous access, and B part is for the hierarchical access. Okay, so yeah, so now let's start with the third question. So third question I want you to give as homework, okay, because we have solved a lot of things. So I will give you the third question as homework. In the next lecture it will be the assignment solutions. I want you to try it out by yourself. So up until now I think we have done enough questions to like give you a basic example. All these I will solve in the next lecture, so you can take a screenshot now. Okay, so I guess this question is interesting. This I will not give you as homework, this we will do. So let's read this question again. There is a term two level memory hierarchy. Two level memory hierarchy simply means I have a cache memory and main memory, that's it. So I will have a cache memory and I will have a main memory, okay, and CPU is somewhere here. This is my CPU. So my CPU is here. Okay, this whole thing got deleted. Okay, oh my god, sorry. Yeah, so CPU is here. Okay, now I have my cache memory here and my main memory. What is the cache memory access time? 15 nanoseconds. So T cache, so this is my cache memory, main memory. So T cache will be 15 nanoseconds. My T main memory equals to 110 nanosecond, and the hit ratio is what? Hit ratio is 90%, so it is 0.9. Hit ratio is 0.9. Okay, these are the information. What else they have told me? The cache block size is 16 bytes. So block size is 16 bytes. Block size is 16 bytes. So now they are asking me what is the average memory access time. How do I find out the average memory access time? So basically what you will do is, and also they are considering the miss penalty, like what is the average memory access time including the miss penalty. What do I mean by miss penalty? So miss penalty, right, is just another synonym for hierarchical access. So it is just another synonym, another way to tell that you are using hierarchical access. Hierarchical access. Why? What do you mean by miss penalty? So miss penalty basically means if I have missed, right? If I have missed, I have to pay a penalty. So basically, what happens in the hierarchical access? So first RAM goes to the cache memory. As it is a miss, then RAM tells now you start, now Sam start. So this part is the penalty, right? I have to waste my T cache period of time penalty to check whether it exists on the cache memory or not. Both of them could have started simultaneously. So this is the time wasted. So here time wasted in checking the cache memory. So as there is a time wasted in checking the cache memory, that's why it is called miss penalty. Miss penalty in this case, miss penalty will be what? Miss penalty will be just T cache, because Sham had to wait for T cache period of time for Ram to know whether that particular data address exists on the cache memory or not. So we will use hierarchical access time. So my T average will be what? It will be H times the T cache, H times the T cache plus H times T cache plus 1 minus H into T into like miss plus T cache, the miss penalty. So this is the miss penalty, basically miss penalty, and now plus it will be T block, right? The transfer time required to transfer the block of data from the main memory to the cache, plus again the time it requires to write back to the cache memory, right? I have to write back that data into the cache memory. So plus T cache. So what is T block? T block will be block size 16 into the main memory size 110. So it will be 1760 nanoseconds. Okay, so ultimately my value comes out to be my T average comes out to be hit ratio. Hit ratio is 0.9, I guess. It is 0.9 into T cache. What is T cache? T cache is 15 nanosecond. Plus 1 minus 0.9 into T cache. T cache is 15 nanosecond plus the block transfer time, that is 1760, plus the T cache 15 nanoseconds. So it is 1790. So this answer will be, if I calculate, this will be equals to 1790 into 0.1. So this will be plus 179, and this will be equals to 0.9 into 15 equals to 13.5. okay, so this will be this much nanosecond. So this will be 179 plus 13.5, so 192.5 nanosecond. So this will be the answer for this particular question. So this is a very good question. Just miss penalty was the new word. I hope now you have understood what does miss penalty means. Basically the penalty that I have to pay for every miss, right? So that is the miss penalty. Now let's understand a bit about cache write policies. What do you mean by cache write policies? So cache write policies basically means, let's say I have my cache memory and I have my main memory. Okay, so whatever is this value x that is stored here, same value will be in the main memory, right? Say from the main memory only we got this value in the cache memory, correct? So my CPU is here. So my CPU actually now wants a certain thing. CPU tells that actually I need to update this value. I need to change this value. I want to update this value. It can happen, right? So let's say previously this location used to show the like addition. of two things. Now the values have changed, so addition will also change. So I want to update this value from x to y. I want to update this value from x to y. So if you have updated in from x to y, right, you have to update that in the main memory as well. Why? If you don't update in the main memory, and if you just only update in the cache memory, so once, let's say I do some replacement, this cache thing goes away from the block, this goes away and new blocks are entered, and once I need this value y, this is not present in the cache, so I'll go into the main memory. Cache memory will see x, CPU will see x, but am I supposed to see x? No, I was supposed to see y because I have updated here y, right? So actually when I update any value in the cache memory, I have to go into the same location on the main memory and update the value. So that is what is written over here. When CPU updates a value in the cache, it must ensure the main memory is also updated. Two primary write policies are used to handle this. So there are two types of write policies that used to handle this, this updation. One is write through policy. How is write through policy used? So data is written both in the cache memory and main memory simultaneously. So immediately after you instructed CPU that I want to change the value from x and y, so both happen simultaneously. That is immediately they happen. That as soon as you change in the cache memory, at the same point of time the value will be changed in the main memory as well. So ensures data consistency between cache and the main memory. What are the advantages? So the advantages here is it is consistent data between cache and memory. So there is consistent, there is no inconsistency, right? Between cache memory and memory, there is no inconsistency. As soon as you update the data in the cache memory, you also go into the main memory as well and update the data. So it is very simple to understand, and it is very simple to understand as well. It is very simple to implement and very simple to understand this. What is the disadvantage? Disadvantage is slower performance as every write operation accesses the main memory. So like the advantage, right, of cache memory goes away. Why? Because as soon as I do any modification in the cache memory, as soon as I write something in the cache memory, I have to go to the main memory and write it. So of course I hope you remember that going to the main memory is a task, because main memory is further away from the CPU. So that's why it will take me more time, right? Every time there is a change in the cache memory, I have to go to the main memory and change it. So it costs time. That is the disadvantages. Okay. So even if there is hit, right? Even if there is hit, still we have to go to the main memory. What do I mean by it? So here if you see, the average read time and average write times are different. Average read times and average write times are different. So the average read time is very simple, right? Average read time is same as the previous one because I don't have to modify anything. I don't have to modify anything. Whatever was the previous average read time, that is the same here. That is the same. Okay, this is same. This does not change, right? Read time does not change. Read time does not change. Does not change. Okay. What is the average write time? What is the average write time? So the average write time, right, will be the maximum of T cache and T main. Why? Because if it is right, I just have to either go to the cache memory and change it. So whenever I go to the cache memory and change it, I have to simultaneously go to the main memory as well, right? Write means I'm writing something. So write means CPU can write to the, like, let's say if it is not present in the cache memory, whatever, like let's say I want to change the value of location 110, that is not present in the cache memory, so I will directly go to the main memory and write it. Great, got it. That how much time will that take? That will take T main, right? Time taken to access the main memory. That's it. What about if it is a hit? If it is a hit, then I have to go to the cache memory and change the value. Let's say location 100 is there, that is present in both cache memory and the main memory. So whatever data was present in the location 100, that is present in both main memory and cache memory. So in the cache memory, what is happening? I will go into the cache memory. I will go into the cache memory. I will update the value from x to y. I will update the value from x to y. Okay. Next what I will do? Next, uh, next I have to go to the main memory as well, right? I have to go to the main memory as well, and I have to change it from x to y. So how much time it took me to access the cache memory? T cache. Okay, so it is simultaneous. So the instant that I start to update, so Ram will go to the cache memory and update the value. In the same instant, Sam will go to the main memory and update. So it will take me the maximum of T main or T cache, whichever one is the higher. That will be the overall time to write to the memory, right? Whatever, whether it is cache or main memory. That's why the T average write time will be the maximum of cache memory or main memory, maximum, whichever one is the higher. So I hope you have understood this point. What will be the overall T average? Overall T average will be the average of those two, right? It will be read fraction, that is the, like, let's say I have 100 operations, right? Read write operations. Out of 100 read write operations, 60 are of read type and 40 are of write type. So it will be 60 times the T average of read into 40 times the T average of write. Same concept as the hit ratio. Okay, similar concept as the hit ratio. So I hope you have understood the basic concept. Basic concept is whatever data data is updated in cache memory should be same should be same should be updated in the main memory. Okay, so this is the main crux of the concept. Just give me 1 second. So let's solve a question from this, right? So a system uses write through cache with an write through cache means it uses the cache write policy as write through cache. So there is other policy as well that I will discuss. So first of all, let's understand this. It uses write through cache. Write through cache means that whatever I update in the main memory, sorry, whatever I will update in the cache memory, I will instantly go into the main memory. So my, from this line, from the first line, directly I can say the time for T write will be what? Time for T write will be maximum of T cache, comma, T min. Okay, maximum of T cache, comma, T min. Okay, so generally most of the cases it will be T min only, right? Most of the cases it will be T min only, because of course cache memory time will be lower, maximum number of cases. Okay, so that is fine. With an access time of 120 nanoseconds and a hit ratio of 85 seconds. Okay, basically a system uses write through cache with an access time of 120 nanoseconds. Basically this is telling me the cache access time. Okay, so access time of 120 nanoseconds meaning write through cache, meaning access time of the cache. So T cache equals to 120 nanoseconds and a hit ratio of 85%. So hit H equals to 85%. So this will be equals to 0.85. Okay, so hit ratio will be equals to 0.85. So now what I can say is the main memory. So this was for the cache memory. The main memory access time is 600 nanoseconds. From this line also you can understand, like this 120 nanosecond was for the T cache, if you have any confusion. So the main memory access time is 600 nanosecond. So T main memory will be equals to T main memory will be equals to 600 nanoseconds. Okay, and 75% of the memory references are read operation. So read percentage equals to 75%. Read percentage equals to 75%. Okay, so this is equals to 0.75. Got it? So this is equals to 0.75. Now what I can say is, how many write operations I have? Write operations is 0.25, right? So what are they asking? They are asking to calculate the average memory access time for read operations only. So let's first of all find out the T average. Okay, T average for read operations only. What is the T average for read operations only? Okay, so the T average for read operations will be what? First of all, it is a read operation, so I don't care if it is a read. I don't have to worry about this write through cache, all those things. Ignore it. If they are only asking for read operation, if it is a hit, the time taken will be T cache. If it is a miss, the time taken will be what? They have told me, right? Okay, memory references. So actually here, they should have, like here they have not mentioned any penalty time. So no penalty time is getting mentioned, and if nothing is mentioned, right, by default you will assume simultaneous access. So if nothing is mentioned, so I will write here, if nothing is mentioned, generally we assume simultaneous access. But for standard questions, don't worry, it will be given whether it is simultaneous access or hierarchical access. For standard questions it will be given, you don't have to worry. So here my T average read will be what? T average read will be H into T cache plus 1 minus H into the only the access time required to the main memory, right? How much time it required for me to access the main memory, that will be the access time, because here they have not given me any block size, nothing. No block size, nothing has been given. So it will be just the access time of the T main memory, that's it. Okay, so this will be equals to what? H is the hit ratio. Hit ratio is 0.85 into T cache. T cache is 120 nanoseconds. 120 nanoseconds plus 0.15 into T main memory. T main memory is 600 nanoseconds. So this will be 0.85 into 120 plus 0.15 into 600. So this will be 192 nanoseconds. So 192 nanoseconds will be the average read time for this particular system. Okay, for this particular system 192 will be the average read time. Now let's understand the next one. Calculate the average memory access time for write operations only. So for write operations only, as we are using write through cache, this is the first one. As we are using write through cache, so it will be very easy, right? Write through cache is basically T write average will be maximum of T cache comma T main memory. It will be equals to, so maximum of T cache and T main memory. So T cache is 15, I guess. Yeah, it is 120 and T main memory is 600. So maximum will be 600 nanoseconds only. Okay. Now what they are asking? Now let's read what they are asking. Now they are asking the calculate the average memory access time for both read and write operation. What is the average memory access time for both read and write operation? So I know the average memory access time for read, I know the average memory access time for write. Simply what I have to do, I have to multiply by the read percentage and the write percentage, and that will give me the T average. This will be read percentage into T read average plus write percentage into T write average. Okay, so simple, right? Read is what, 75% of the time we are reading and 25% of the time we are writing. So it will be 75, that is 0.75 into the T read average. T read average is 192 nanosecond plus 25% of the time we are writing, so 25 into T write average. T write average is 600 nanoseconds, so this will be equals to 0.75 into 192 plus 0.25 into 600. So this will be 294 nanoseconds. Okay, so 294 will be the average access time. Now what is the next part they are asking? They are asking me the what? They are asking me the effective hit ratio. So what do I mean by effective hit ratio? So effective hit ratio, right? Actually, what is happening effectively? So if I see that there are two things, right? CPU is here. CPU wants a particular block of data. So either CPU will first of all perform the read operation or write operation. Okay, if it's a read operation, the read can be hit or it can be a miss. Okay, read can be a hit or it's a miss, right? Hit means it is present in the cache memory, it is not present in the miss means it is not present in the cache memory. So if it is a hit, then in this case only cache memory is accessed, and if it's a miss, then what happens? If it's a miss, then basically the main memory is accessed, and here, right, they have not told us whether like how we will store the data or something. So only the main memory is accessed, that much I will write. Block size they have not mentioned, so I will not write it. But although in practicality I know that we will store the block in the cache memory as well, but here they have not mentioned the block size, so I will ignore the fact. This is for the read operation. What about the write operation? So in the write also there can be two things, right? Either it will be cache hit or cache miss, right? If it is already present in the cache or if it is not present in the cache. If it is not present in the cache, main memory will be accessed. Correct? But if it is present in the cache, will I get any advantage? I will not get any advantage. If it is present in the cache, I will update the value in the cache memory, but I have told you we are using write through policy. In write through policy, whenever I update the value of cache, I have to go to the main memory as well to update. So this will use the, like, again in the hit as well, main memory will be accessed. In the hit as well, main memory will be accessed. Okay, so yeah, that is the thing. So basically, right, it does not matter if it's a write operation, does not matter. I don't get any advantage with cache hit. So effectively, right, there is no advantage. That's why the effective hit ratio will be lower. That's why the effective hit ratio will be lower, because here with the hit I am getting an advantage, here with the hit I am not getting the advantage. So the effective hit ratio basically only takes into account the reads, it does not take into account the writes. So basically the answer D, the effective hit ratio is just the effective value of hit ratio. So it is E effect, that is it only takes the effect of reads, because with writes I am not getting an advantage, even though the hit is there, right? Even though there is a cache hit, but it is not giving me any advantage. So what is the effective hit ratio that is actually giving me the advantage? So it will be number of reads percentage into the actual hit ratio. This will be what? Percentage read is 0.75 into hit is 0.85, correct? It is 0.85. If you see, it was 0.7, like this is the read percentage, and okay, sorry, this is the read, what is the hit ratio? Yeah, hit ratio is here, right? Hit ratio is 0.85, read percentage is 0.75. So read percentage is 0.75, read percentage is 0.75, and hit ratio is 0.85. So this will be 0.75 into 0.85. So 0.75 into 0.85, this will be 0. 0.6375. This is the effective hit ratio. So so I hope you have basically got the idea. You have got the idea. Now there is cache write policy as well. I don't think this lecture has already gone long. So what we will do is I will discuss about the cache write policy, cache write back policy in the next lecture, and there are few questions which we will discuss in the next lecture. So we will discuss about all these things in the next lecture. So because this lecture is already gone very long and I don't want to extend it any further, so we will understand this write back policy in the next lecture. So I hope you have enjoyed this lecture. If you did, please make sure to hit the like button. Please comment down below which portion you enjoyed the most, and if you are enjoying this whole playlist, make sure to comment on the first video as well of this playlist how much you are enjoying this COA. So I hope you have enjoyed this video. In the next lecture I will see you in the next lecture. Until then, happy learning.